46, right? Yeah. This is page 46. Just a real quick reminder from 8th grade. You learned what? Do you remember? We said this was 8th grade. Linear functions. You learned linear functions in 8th grade. That looks like this. How do I know that's linear? This is an understood 1 right here. This is what tells me it's linear. In 9th grade, your current grade, we're going to learn quadratics. Quadratic functions. How do I know when I have a quadratic in front of me? Thank you. You're on it. Here is an example of a quadratic function because it is to the power of 2. Okay, the degree is 2. Degree is the word to describe the highest exponent. We're looking at quadratics for the next several weeks, okay? So, it's very important that you understand when you hear a quadratic that you associate it with a function that has a leading term of x squared, okay? Now, there's a lot to learn about quadratics, a lot. So we're going to dive right in, and then we're just going to start practicing, okay? The good news is these formulas are on your formula sheet. So you don't have to memorize the formulas. You do have to memorize the vocab words, what the parts mean, and how to find it, okay? So first, before we start actually graphing them, let's talk about the different characteristics of quadratics. First, you see this curve? I'll change colors and try to highlight it. You see this? Nice curve right through here. Okay, first of all, I would like you to put arrows on the end because it does continue on. And then now what we're going to do is look at the different parts. Do you notice a dotted line right down the middle? You see the dotted line? This is called your axis of symmetry. Your axis of symmetry is where you could take the graph and fold it hot dog style. Everybody look at my paper. You fold it hot dog style, and the dotted line would be the crease in the paper, okay? So imagine taking that and folding it hot dog style, and then the crease in the paper would be the dotted line. It's right in the middle of the quadrant, yes.
I don't have that paper. I only have this one.
That would be because your buddy failed to pass it down. Thank you for letting me know. So it goes right down the middle of the quadratic curve, okay, every time, every day, all day. The axis of symmetry goes right down the middle. And the reason it goes down the middle is because it creates this, it shows you the symmetry. Focus on me. The left side would match the right side if I was to fold it. Do you see that? So you got axis of symmetry. The next part, vertex. Notice it's pointing to the very, very bottom of the curve. The absolute lowest point on this curve. Now, I just want to see if by curiosity you can answer me. If the curve was facing down, what do you think the vertex would be? Negative. Well, I mean, where do you think it would be? So here the curve is facing up, right? And the vertex is right here. Now imagine if it was reflected down.
It'll be -3.
It'd be at the very, very, very top, right? So the vertex can either be the bottom or the top. Let's go even further. It could be the lowest or the highest. It's always one or the other. I'll say it again. It's always the lowest or the highest. The words we're going to use are max or min. It's always the maximum point or the minimum point every time. And it's always right through the, what did we just talk about? Do you notice the axis of symmetry always passes through the vertex? That's because the vertex is in the middle of the curve every time. Y'all with me? It's rare that I get to say, hey, it's like this every time. With quadratics, that's why I like them. There's a lot of stuff it's like that every time. Okay? So the axis of symmetry, let's make a note, will pass through the vertex every time. And the vertex is either the max or min. It just depends on which direction the curve is opening. There's another important aspect. It would be these dots right here. What are those dots sitting on? Thank you. This is the x-axis. Do you notice that those dots are sitting on it? Right? They're on the curve, and they're on the x-axis. All right. Now, this box is bigger because there are 4 words to describe those points. 4 words. So you might want to wait and see what all we got to write and decide how big you need to write. Those are called the x-intercepts, which are also called the roots or the zeros. But oftentimes we say the solutions. There's a lot to put there. All 4 of these words mean the same thing. I have no clue what the state is going to use. You have to know all 4. Now, that's the bad news. The good news is some of them are self-explanatory. X-intercept. Well, this is where the graph is crossing or intercepting the x-axis. So this makes sense. You've dealt with x-intercepts before. Solutions. You're going to learn as we're solving quadratics that it's where the graph is crossing the x-axis. Those are the solutions. If I was to take, like if I knew the function, and if I was to solve for x, it would bring me to these 2 numbers that are these points here. Zeros is one you're just going to have to memorize. What are the zeros of the function? That's a fancy way of saying, hey, what are the solutions? What's the x-intercepts? Where is it crossing the x-axis? You can put it in Desmos and you can find it. Roots. Where did the roots of a tree grow? On the bottom, on the ground, right? I want you to think of this is this. Oh my word. That's blue. It looks really purple. All right, let's try this. Can we get a brown? This may be silly. All right. So we have a tree, right? You with me? We have a tree. Yay! Like Bob Ross, a happy little tree. Okay, and then we have the I think you'd like a different color for the ground. Here's the ground, I guess. There's the ground. You with me? Okay. Where do the roots grow? When a tree grows into the ground, right? The roots grow in the ground. I want you to think of the tree meeting the ground. Those are the roots of the function. Where the tree, where the graph is touching the x-axis. So think of like up here is the tree and then down below is the ground. So that's one way to visualize what the word roots means. Just think of like the roots of a tree grow in the ground. Where's the curve touching the ground? So think of this as the ground. Okay? You and me? Yes? Now, those are the most important characteristics. There's more to come, but that's the most important. The entire graph itself is called a parabola. The whole curve is called a parabola. So if I say we're graphing parabolas, it means we're graphing quadratic functions, and they're going to be a curve, okay? Now, quadratics can be presented in two different formats. There's what's called standard form. That was hideous. Standard form or vertex form, okay? Two different formats. Turn to page 3 in your notebook. Flip to 3. I think it's 3. No, it's that page right there to the left. Maybe it's 4. That's it. Is that 3? It should be the hot pink one. Please locate the formula. Is that 3 or is that 4? Locate the formulas for the quadratics on there. You will notice. Oh, they gave us 3. We'll do a whole other sheet. I'll just worry about that later. They give us 3 different formats. Standard form, vertex form, and then factored form. Let's see, we could put factored form right here just so it's all in one place. The factored form of quadratic is this. According to your formula sheet. You can write it right there. The 2 most important ones are standard and vertex. Factored form should look familiar because you see the parentheses. You see the binomials. Do you see now why we just came off of last week's lessons? Factored form is more helpful like when you're graphing it and being able to recognize the roots. All right. But standard and vertex form are the ones that are used more often and like broken down and dissected more, okay? When it's in standard form, this should look familiar because we used to rearrange polynomials in standard form, right? So this is old news. So this is in standard form, degree 2, it's quadratic. What is the leading term? 2x squared. Terms the whole part. 2x squared. What are the coefficients A, B, and C? What would A be? 2. What's B? 5. What's C? -3. It's very important you understand how to get A, B, and C. We're going to eventually get to the point where we can talk about what this quadratic is going to look like in a nutshell based off of just A. Like I can tell you right now that this quadratic is opening up and is getting stretched. And I know that just because that's a positive 2. So that's the goal. We're going to get to that point where you can look at it and be like, okay, it's definitely opening up and it's going to get stretched, so it's going to be kind of skinny. Unlike that one where it's kind of just a normal curve. It's going to get stretched. Okay? Vertex form. The reason vertex form is called vertex form is because you can actually see the vertex. Remember we said the vertex is the either minimum or the maximum. Like this vertex is -1, -3. If it were in vertex form, it would be right here as H and K. The vertex is, I want you to put an asterisk, H and K. The reason we're putting an asterisk is because there is a sign change. And it's because there's a minus sign in vertex form. Now, I want you to look at this formula compared to this formula. What do you notice is different?
The square outside the parentheses.
The squares on the outside of the parentheses here. And what's the same in there? What variable is the same? A is in both. AX squared, and then here there's an A in the front. Do you notice that? Eventually, the goal is we're going to learn how to switch from one to the other form. You can probably see where this is going, and now you understand why the last 2 weeks we spent multiplying polynomials and factoring them. If I want to go from this form to that form, I simply multiply out that binomial squared, and then distribute the A and then add the K. If I want to go from that form to that form, I'm going to write it in factored form. So I'm going to have to learn how to factor it. Okay? I'm showing you kind of like a game plan of where we're going. There's a lot to learn about quadratics. Now, real quick refresher. We're talking about the parent graphs, or mother functions, I call them. Linear was 8th grade, remember? This was 8th grade. The parent graph for a linear function splits right through the middle. I'm so close, like the graph is jumping. Just do the best you can to split it right through the middle. Now, a quadratic parent graph, meaning this is the graph of the curve with nothing done to it. No reflection, no stretch, no shift. It's like the starting graph before you do anything to it. It sits right on the origin. That's where the, what's the vocab word? Starts with a V. That's where the vertex will be. And it opens upward. So if you think about it, and I'm going to try to graph it like by actually hitting the points, but this is so small it's kind of hard to do that. But if you think about it, if I was to plug 0 in here, 0 squared is 0. If I plugged 1 in, I get 1. If I plug 2 in, I get
2.
No.
Wait, no.
2 squared
4.
is 4. 4. If I plug 3 in, I get 9. Assume this is a 10 by 10. So you can see where this quadratic curve is right here. Okay, so that is hideous. So I'm just gonna have to expand it a little bit. You can't really see the curve. We're just gonna do the best we can to show that it's just a nice curve right there on 0, 0. But technically, you know, your T-chart, like if you think about it, your X and your Y, 0 is 0, 1 is 1, but 2 is 4, 3 is 9, and so on. Okay, so this is our mother function. We're going to take this and we're going to start practicing graphing it, talking about the characteristics of the graph, talking about where's the axis of symmetry, why does it always pass through the vertex, and how do you find it? So let's fill this in. Where's the axis of symmetry? Or what is it? It is the vertical line that divides the parabola into two congruent halves. What does congruent mean? Do you remember? Same. Equal. What did we say that the axis of symmetry always passes through? The vertex. And going back over to the vertex form, we said the vertex is HK when it's in vertex form. The formula, so over here, let's make a note, the vertex is HK. The formula for finding the axis of symmetry, it depends on which form it's in. If it's in standard form, it's x equals negative b over 2a. Don't worry about what that means right now, just write it. You'll learn what it means when we start practicing it. This paper is to serve as a one-stop shop of all the information you need. When it's in standard form, it's negative b over 2a. But when it's in vertex form, x is simply the h value. X equals h. All right. Hoy-Vux comes back into play here. Do y'all remember Hoy-Vux from a few weeks ago? The acronym was to help you remember how to quickly draw a vertical or a horizontal line. It says graph a quadratic with x equals 4 as the axis of symmetry. If it's x equals 4, which scenario do I have? Hoy or Vux?
Is it vertical?
If it's x equals 4, which scenario do I have?
4. Vux.
Vux, right? Because doesn't Vux have the x in it?
Yep.
Does that make sense? Line up the x's. So this is going to be a vertical line on the x-axis at 4. So here's the x-axis. Let's find 4. It's right there. And we're going to drop a dotted line to serve as our quadratic function. Right? So this dotted line is the axis of symmetry, x equals 4. Now it says graph a quadratic here. You can graph whatever you want as long as the vertex is on the, what? It's got to be on the dotted line because that was your axis of symmetry. So you could graph one down here and give it a curve, or you could graph it up here and curve it down. What do y'all want to do? You want to try one curving down? So just put your vertex anywhere on that dotted line and then draw your curve as symmetrical as possible. Tear off extra credit.
I don't even know what that is. I probably won't end up having one.
Okay. All right. Now let's talk about the vertex some more. We said that the vertex is the blank or the blank part of the graph. Do you remember?
The top.
We said it's the minimum
Yeah, minimum or
or
max.
maximum part of the graph. Minimum would be if it's opening, which direction? If it's opening up, it has a minimum. So if it's opening up, it has a minimum. If it's opening what? It has a maximum. If it's opening down, it has a maximum. Can you have both on a quadratic? No, not possible. The y value of the vertex is determined by simply plugging in the AOS here stands for axis of symmetry. They're saying this axis of symmetry, they're calling it AOS on the rest of the sheet. So y value of the vertex is determined by plugging in your axis of symmetry, which was your x value of the vertex, okay? So the y value of the vertex could be k, the k part, because notice the vertex is hk. H is your x coordinate, k is your y coordinate. So if it's in vertex form, this right here, I'm gonna make a note. If it's in vertex form, it would simply be y equals k. If it's in standard form, you have to do a little bit of work. You got that whole negative b over 2a. You would plug that back in, okay? You would find f of negative b over 2a, which means you took the x coordinate that you already found and you would plug it back into the function, okay? Again, this paper is serving as a one-stop shop for all the information. Notice we've not really done a practice problem yet to put it all together. So right now it may feel like you're learning a new language. That's to be expected, okay? It'll start clicking when I start saying, here's our example, let's go through it. Now, how do you know if a parabola opens up or down? It all revolves around A, the negative, positive or negative. If A is positive, it's opening, what do you think? Up. If A is negative, it's opening down. It's as simple as that. So if it's opening, we're putting it all together here. If it's opening up, we said it would have a min or max. We said it would have a minimum. And that's exactly where the vertex falls. Did I spell it wrong? Minimum. Where? I did spell it right. Y'all, if you stare at that word long enough, it doesn't look right. Minimum. Minimum. If A is negative, so it's opening down, then it would have a maximum, and that's where the vertex would be. Now, here's two examples. Notice it says, again, parent function, because there's nothing done to it. It's just x squared, right? But what's the understood number in front of it? There's an understood 1 there. So A is 1 here. There is no B. There is no C. So we're going to graph this. Now this time the graph's a little bigger, so I feel like we can do it justice. The vertex would be 0, 0. How do I know that? A couple of ways. Let's see. I'm going to shift this over. Let's write it right here. I'll show you how to write it in vertex form. So it'd be f of x equals a, parentheses, x minus 0 squared plus 0. Now write that. Looks kind of weird, doesn't it? What happens when you subtract 0? No, when you subtract 0. What happens when you subtract 0? Nothing. Right? If you subtract 0, think about it. If you subtract nothing, will anything change?
Nope.
Nope. What happens when you add 0? Nothing. So I just took the standard form and I rewrote it in vertex form to show you that the vertex is 0, 0, because there was nothing there. Okay? Now let's plot it. We said if you plug 1 in, you get what? 1 squared is 1. 2 squared is 4. 3 squared is 9. Now, the axis of symmetry goes right down the middle. I don't need to calculate the other side. I can just mirror image it. Reflect it over. So there's the rest of my curve. And then now I'm going to do the best I can to make it look like a curve and not a straight line. All right, I want you to try this one. Notice this one says negative x squared. Hampton, wake up. This is an understood negative 1, so A is a negative 1 here. Watch what happens to our graph. It's still at 0, 0. Now, if I plug 1 in, I get 1, but then there's a negative 1 in the front. So what's negative 1 times 1? If I plug 2 in, I get 4, but there's a negative 1 in the front. So what's negative 1 times 4? Negative 4. If I plug 3 in, I get 9. But there's a negative 1 in the front. Negative 1 times 9 is negative 9. You can see where the curve now is opening down. To graph it, again, I really only have to graph half of it, and then I mirror image it. You're also going to have Desmos at your disposal. So Desmos is going to be very helpful here. In fact, we are now at our examples where we're putting it together. We're going to do these 2 examples, and then we have like a special what-if scenario, and then class will be over. You'll have a Delta Math assignment to practice graphing. So go ahead and get Delta Math out. Go ahead and get your Desmos out so you can be practicing this, okay? Typing it in. We're going to look at these examples. By the way, this is page 47. You may want to keep your notes out. It says, use the formulas to determine the vertex and the axis of symmetry for the quadratic equation. Then draw a rough sketch of the parabola. Now, I'm fixing to compromise everything I hold true and valuable for teaching. I believe you need to know the math. I believe you need to know the algebra behind it. Okay? However, I told y'all on day 1, I also think you need to know how to be a test taker. Because unfortunately, you do have a high stakes test looming over you. My name goes on your grade. So I'm also, right up there with you in terms of a high stakes test over me, except you take it. I have no control over how you answer. Quit humming. So what I want to do is show you just how easy it is to answer this question with Desmos. But then I want to challenge you to learn the algebra behind it. Okay? Because the algebra behind it is what's going to carry you through Algebra 2 and Pre-Cal. We do stuff like this in the college level math classes. All right? So, I'm going to say it again. I'm going to show you how, it's not cheating because Desmos is right there on your DRC Insight. I showed it to you. It's at your disposal. So it's using your resources, right? But I also want you to try to learn the math. I need you to put the math on paper. So go to Desmos, and I want you to type in the function exactly how you see it. Can someone read it to me?
Equals x to the power of 2 plus 10x
Plus 15? Okay. You may have to adjust to be able to see it, right? I would get it to where you can see the vertex and the zeros, the roots. Okay, so we have it in Desmos. Do you notice how on Desmos you can put your cursor on the curve and it reads to you the points? Do you see that? Do you notice how I can get down here to the bottom and I just have to move carefully and I can read my absolute lowest y value is -10. -10 happens right there. What do you think what part of the curve is that? That's the vertex, which is also the minimum. So, winner, winner, chicken dinner, I immediately know the vertex is -5, -10. Now, you do have to be careful there because you have to make sure it's the lowest, right, or the highest. So you have to move that cursor carefully to be able to read, like, where is the absolute lowest value. So the vertex is -5, -10. Now it says, what's the axis of symmetry? Going back to that other piece of paper, we said that the axis of symmetry always passes through the vertex. Once you find the vertex, you've got the axis of symmetry. Now you do have to be careful because they want it as an equation of a line. Hoy-Vux is helpful here. The axis of symmetry for every quadratic should run in what direction? Because we said quadratics are either up or they're down. So what direction should your axis of symmetry always run? Up and down. So is that vertical or horizontal? That's vertical. So is that Hoy or Vux? That's Vux. So what is the equation of the line that drops right down the middle here? X equals -5, because it's literally telling you it's X Vux, right? It's the X value. So X equals -5 is your axis of symmetry. Now let's find our A, B, and C. What's A?
1.
What's B?
At 10.
What's C?
15.
Now we're going to do our best to copy this here. So we got -5, -10. It's going to be right there. We have our axis of symmetry. And it's opening what direction? Up. Now look at your x-intercepts. Notice they're not pretty. Right? This is not right at -2. And notice this is not right at -8. So when we put this on our paper, try to copy that. Try to be just outside of -8 and just inside -2. Don't try to go right through it. So -2 is about right there. So it's going to kind of come like a little outside it. This is 10, 9, 8. So it's going to come a little outside that one. Well, I did the best I could. Do you notice how I don't have anything on my paper algebra-wise? All of that came from Desmos. Now, the algebra behind it. How about this? Because of what time? You try number 2 real quick. I'll show you the algebra tomorrow. Try number 2 using Desmos. Tell me the vertex and the axis of symmetry and answer A, B, and C. Yeah. Great question. Type it in, find the vertex, write the equation of the axis of symmetry. Do what? Keeps on going. You can always hit this home button and it'll zoom back into the normal viewing window. And then now zoom out carefully. There you go. So now you can find it. Well, you went too far. You'll have to, see, you have to play around with, so let me show you. You can zoom in right here. And then now you can start dragging to find it. What'd you get for the vertex, y'all?
-5, -10. Or -2, -7.
So what's the axis of symmetry?
-2.
Very good. I'll post you just a couple of problems where you're doing that, okay?